So we'll get started here and jumping on into this material. So this is chapter 3, and I told you a while ago I love chapter 3 because it is kind of the heart and soul of everything. Also because we start talking about functions, and functions have to be fun because why else would they have the word fun in there? So anyway, I'm just telling you, they're fabulous. So we're going to be talking about relations and functions today, having to do with math, not personal relationships. Y'all can deal with those on your own. But we will talk about these relations and what makes a relation a function. So essentially, a relation is any set of ordered pairs that you might have. We've looked at circles. Circles are great relations. They are not functions, however. We've graphed some equations, which turned out to be functions. We'll discover later on. But anytime you can create a set of ordered pairs, you have some type of relation. And in those ordered pairs, we have two components. So our ordered pairs consist of an x part and a y part, or a first value and a second value. And the set of all first values is called our domain, or the x values, and the set of all second parts, or y values, is called the range. Now, the reason we use first component, second component, is because sometimes we get ordered pairs that are like A, B, and strange things like that. So, but typically it's x and y because we're graphing on a coordinate system. If you have a very special relation where each value in the domain corresponds to only one value in the range, in other words, there are no repeated x values, right? We'll talk about that in a second, then this particular relation is called a function, okay? So in other words, if you have a set of ordered pairs where you have two different ordered pairs that both have an x value of 3, that's not going to be a function, okay? Because that 3 is trying to pair with multiple y values, and that's not cool, okay? So in terms of being a function, you're not going to have repeated x values in your ordered pairs. So the last thing I want to tell you, just kind of in general information, is absolutely every function is a relation. There's a bunch of relations out there that are not functions. And a circle is actually one of those. It's a beautiful relation. It makes a beautiful graph, but it is absolutely not a function, okay? All right, so let's get started with these. The very first thing we want to do is just simply look at a couple of sets of ordered pairs, determine whether or not those ordered pairs represent some type of function, and then identify the domain and range. And we'll continue to add to these concepts of function and domain and range as we move through this material. So the first one here is the set of ordered pairs. There's 5 ordered pairs in here. And what you want to look for to determine whether or not this relation is a function is, are there more, or is there more than one ordered pair with the same x value? Can anybody tell me if this set of ordered pairs has repeated x values? And you can chat to me. You can tell me what the x value is if there is one. You can say, no, there's not, or you can answer me out loud.
I see 1 as a repeated pair.
Yep, that is it. And that's all it takes. Because I have 2 ordered pairs with the repeated x value of 1, this is what makes this not a function. And that's all it takes. All it takes is 1 repeated x value. So this is not a function. However, it still does have a domain and range. And so the domain is, and it's always going to be written in a little set bracket notation, is the set of the x values. So -1, 0, 1, 2. Notice that since 1 is a repeated x value, I only list it once. And even if I had like 20 repeated x values, I would only list each one of them one time. I don't list them repeatedly, okay? The range for this function is the y values. And so as I go through my y values, I have 5, I have 2, I have a repeated y value, but we weren't concerned about that. That's just another something else that could go weird, but it's not going to affect whether or not this is a function, but I just don't write it but once. Then I go to 3, and then I have 7. And so this is my set of range values, okay? So not a function because I have repeated x values. Domain is the list of x values. Range is the list of y values. What about number 2? Are there any repeated x values in number 2?
No.
No, there are not. So this is a function. So this particular set of ordered pairs does represent a function. So that's a good thing, right? So we've identified that because I can go through and each x value is its own little thing. And so now I can list the domain, and that domain is the x values -1, 0, 1, 2, and 3. I usually typically just list them in the order that they're written. It does not matter. MyLabs is not going to care what order you list them in. If it's multiple choice, they might list it in numeric order or they might not. But if it's just typing in the answers, it doesn't matter. The range is the y value, so I have 5, I have 2. Again, that 5 is repeated, but that's not going to affect whether or not it's a function. I just don't write it more than once. And this 3 and the 7. And so those are my domain and my range and the fact that this is indeed a function. Questions? Okay, excellent.
I have a question.
Yes,
Okay, will the domain always be your x values and the range always be your y values?
yes, that's exactly right. The domain, and the reason, and to me, it makes it really easy to remember. I'm all about the alphabet. But X comes before Y in the alphabet, and domain comes before range. So the domain is the first values, and the range is the second values, and that should help you keep them straight in terms of just making that association. But yes, you spot on with that. Domain is all the X values, range is the Y values. Perfect. Very good. Other questions? Okay. All right. So now we're going to talk about what a function actually is. We're going to look at a function in terms of the graph. We're going to look at some relations in terms of graphs. But in terms of like the rules for these, I'm going to tell you what we're going to have is going to be functions. So a function really is that. It is a rule. It is a rule that defines the operations that you do on a number or a set of numbers or some type of algebraic expression. And I'm going to show you what I think is the easiest, most foolproof way to evaluate these. And you may disagree with me, and that is your right to do that, but I'm still going to show you the way I want you to do this. But like I said, the function by definition is going to give you a rule, and we typically name functions by calling them f of x. That's just the notation that we use. And this is saying my function is named f, the variable I'm going to use is x, and so here is my rule. Now my rule for this problem number 3 says I multiply by 3 and then I subtract 4. Multiplication trumps addition and subtraction, so we do that first and then we do addition and subtraction whenever the order comes in. It is telling us what to do, and that's what a function is. It's just the rule that tells us what to do. So for this particular problem, it says evaluate each function at the given values of this variable and then simplify your answer if possible. So in this case, I'm asked to find f of -3 for this function. Now here's what I'm going to do, and I am going to try to be incredibly consistent on this. I'm going to start off by writing this function 3. In place of x, I'm going to put a parentheses and then the rest of my rule. Whatever the rule happens to be, where I see an x, I'm going to put a parentheses. Now I'm going to do this in a different color. I'm going to drop in this value of x. So this is saying f of -3. So instead of f of x, I'm going to put -3 in place of this x. Now I'm going to evaluate this, okay? And I know that seems a little simplistic, but I think you'll appreciate the fact in just a minute when we start putting something more than just a number in there. So bear with me, write it down like this, giving you time to do it. 3 parentheses -4, and then drop in your -3, okay? All right, so now I'm going to simplify this, and that's how I evaluate. So this is going to become -9 -4. 3 times -3 is -9, then -4, and this is going to give me a value of -13. Now, because I'm asking you to evaluate this at an x value, just talked about the fact that the x values are our domain and the y values are our range. Well, I don't have a y here, But that's what this negative 13 is, and that's essentially what it is. So in terms of domains and ranges, my function now, what I put in is my domain. So there's my domain, and what I get out is my range. So I can write this as an ordered pair. So this is not what the problem is asking me to do. This is just translating this information into a format that we might could use to graph. But my final answer for this problem is negative 13. Okay, so this is the answer for this particular problem. Evaluate f of negative 3 is negative 13. I'm just taking it a step further with you to help you see the graphs in just a minute. Okay, questions about 3a? Okay, let's look at the second one here. I'm still talking about this function. And so again, I'm going to do 3 and then parentheses minus 4. In place of that parentheses, I'm going to drop in this 1/2 because that's what's here, okay? And now I'm going to simplify this. I get 3/2 minus 4. I know it's a fraction. You can't get rid of it. I'm going to write this as 3/2 minus, and then I'm going to write 4 as 8/2, okay? 4 times 2 gives me 8, all right? So now I've got my nice fraction here. 3/2 minus 8/2 is negative 5/2. And that is my value of f of 1/2. So this is my answer for this problem. I could also write that ordered pair where my x value is 1/2 and my y value or my output or my range value is negative 5/2, okay? So I'm not going to right now. I don't want to confuse life. I did want to do it on that first one just so you saw that connection there. Okay, the last part of this is where I think you're really going to appreciate that parentheses. It's going to keep you out of trouble, so please, please, please try to do this. So 3 parentheses minus 4. I am now going to drop in this entire expression, x minus 5, in place of that x. I don't need the x and the x minus 5 there. That x is my holding ground. It is waiting for me to throw something into it. It's kind of like the bag that sits by your back door that just waits for you to pick it up and throw something in as you walk out, okay? So it's the box that you wrap a present in. It's the whatever you want to, it's the container. So I'm going to erase that x, I'm going to put that parentheses, and I'm going to drop in that x minus 5, okay? And so now I'm going to simplify this, and I get 3x minus 15 minus 5, and my final answer here is 3x minus 19. So this is telling me the value of f of x minus 5 is 3x minus 19. Questions? Questions? Okay, we're going to do some more of these, okay? So the functions get a little bit more complicated. So in this case, it's saying I want to square x, and then I want to add 1 to it. So my rule for my function is still called f in this case, still has the variable x. The rule says I square my value of x, and then I add 1 to it. Okay? So for f of 2, I'm going to have something squared plus 1. And that something that I'm going to square is going to be positive 2. Okay, because that's what my little x value is here. So I'm going to clean this up. 2 squared is 4, and 4 plus 1 gives me 5. And so f of 2 has a value of 5. Okay. Same thing for f of negative 2. Parentheses squared plus 1. What's going in my parentheses is negative 2. Remember what happens here. This negative is getting squared. And so again, that's going to give me a positive 4. Plus 1 is equal to 5. So f of negative 2 also has a value of positive 5. And that's okay. That's that repeated y value. And we said that was not a problem. So there's nothing doing anything weird or strange here. I can repeat those y values. I can have everything to have the same y value. It would be very boring, but I can do that. Okay, but that's all I have to do. All right, the next one is where we have to be super careful, okay? And so in this case, again, I'm going to have parentheses squared plus 1. What goes inside this parentheses is this expression x minus 1. Now I'm going to ask you to remember from a couple of days ago, sorry to say a couple of weeks ago, but we've only been here for 2 weeks. So I'm going to ask you to remember from a couple of days ago what we do with x minus 1 squared. Well, that's the same thing as x minus 1 times x minus 1. So we need to FOIL that out, okay? And when I do that, I'm going to get x squared minus 2x plus 1. And then I still have this plus 1 at the end, okay? So this is just x minus 1 squared. Right? Questions as to how I got this. Now is the time to ask this.
Since it was x minus 1 squared, you just FOIL it out and get what's below that?
Yep. So I'll come over here to the side. X minus 1 squared is x minus 1 times x minus 1. And then that's going to give me x squared minus x minus another x, and then plus 1 at the end, which does indeed give me x squared minus 2x plus 1. Make sense? Questions? All right, so I'm going to finish this up, and I'm going to get x squared minus 2x plus 2. And so f of x minus 1 is this entire expression, x squared minus 2x plus 2. Make sure you do simplify it, collect together like terms. Questions? All right. So now we're going to move in and start to use this evaluating functions, and we're going to use it by doing something called the difference quotient. Now, the difference quotient is just combining a couple of things together into a formula, and it is going to be very consistent in how we do this each time. So watch out. Some of the questions at homework have that SBS, step-by-step feature on them. And they are literally going to walk you through the same process that I'm about to walk you through to get to the final answer. Some of them are simply want you to determine the value of the difference quotient for this function. But I'm going to walk you through the step-by-step process. The first thing I'm going to do is I am going to rewrite my difference quotient in colors because I just think it makes it so much easier for you guys to see what I'm doing with that. So my f of x plus h, I'm going to consistently do in a pink color. And then I'm going to have minus. Now I want you to watch really closely. When I write the difference quotient in multicolors, I put f of x in parentheses. That's going to be huge. And the reason is because I'm subtracting this. And it's going to make all the difference in the world to you, I promise. And then all of this is going to be over this variable h, okay? So the first thing I'm going to do is the step of finding f of x plus h. So my function is f of x is equal to 2x minus 5, and I want to find f of x plus h, which means that I have 2 parentheses minus 5, and my x plus h goes in my parentheses. And so f of x plus h is 2x plus 2h minus 5. That's this value right here. That's step number 1. Okay? Nice enough? All right. F of x, and you're going to think this is silly to do this, but we're going to do it anyway. F of x is 2x minus 5. And I'm writing it because I really want to emphasize to you what we're doing here. Okay? So now I'm going to plug this stuff into the difference quotient, okay? So my difference quotient here says f of x plus h. Well, that is 2x plus 2h minus 5. So I'm going to write 2x plus 2h minus 5. And then I'm going to put minus parentheses 2x minus 5, close parentheses. All of this is over h. Now I'm going to stop. I'm going to take a breath. I'm going to make sure you're caught up with me before I do anything else. And if you have any questions, now is the time to ask them at this point. Okay, so now I'm going to clean this up. And I have 2x plus 2h minus 5. I'm going to distribute my negative sign, so I have minus 2x plus 5. Everything is over h. Simplifying as I go. 2x minus 2x goes away. Negative 5 plus 5 goes away. All I'm left with in the numerator is 2h, which is divided by h, and h is divided out, and I am left with 2. And this is the value of the difference quotient for this function. Difference quotient is going to be the same. I will actually give this to you on the test if I want you to use it, okay? May or may not be on the quiz questions because you have access to your notes, but on the test I would be sure to say, determine the difference quotient, and then this would be given to you, and then I would give you a function, okay? And this would be the final answer for this function. And then these are the steps along the way, or some of the steps along the way. Sometimes I ask you to do other stuff too. Okay, questions? All right, let's do another one. Okay, again, I'm going to write f of x plus, I'm just going to rewrite this so that I remember the colors I use mainly. And also just because I think it's good for you to see it and hear it one more time, one more time, one more time. And all of this is over h. All right, so here we go. First part, f of x plus h. Well, it says x squared, so parentheses squared minus 6. In this parentheses goes my x plus h. Now, remember, and we'll do this several times, and so I'm going to make kind of a note over here to the side. If I square x plus h, I am always, this is the same as x plus h times x plus h. And when I FOIL that out and collect together my like terms, I will always get x squared plus 2xh plus h squared. So just a little bit of a time saver. I will skip from x plus h squared straight to this, but I wanted you to see where it comes from. So here I'm going to have this x squared plus 2xh plus h squared, and then minus 6. This is f of x plus h, and this is what I'm going to plug into this formula in just a minute. Okay. Again, just for kind of completion's sake on this, f of x is x squared minus 6. And so now to evaluate the difference quotient, I have f of x plus h, which is this entire expression. So x squared 2xh, h squared minus 6, minus parentheses x squared minus 6. I'm going to clean it up in a minute. I just don't want you to lose that minus sign. Huge, 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 huge. So I have x squared. I have 2xh. Again, I have this h squared minus 6. And now I'm going to change the signs because I'm subtracting everything. Minus x squared plus 6. All of this is over h. If you have done this correctly, every term in the numerator that does not have an h in it should have an opposite. okay? So I have x squared and minus x squared. I have negative 6 and plus 6. And so the only terms I'm left with in the numerator are 2xh plus h squared. And all of this is divided by h. Now, you can simplify this a couple of different ways. I'm going to think of just this h dividing into each of these terms. And when I do that, h divides into this term, leaves me with a 2x. And h divides into h squared, leaves me with an h. And so this is my difference quotient for this function. Questions? Okay. So we're going to do one more of these just because I think this is a huge kind of concept and I just want to make sure that you really understand how to do it. This one is different because I have two x's in it. All of the previous problems only had one x in them. And so that makes this one just a little bit different. Still, my difference quotient is f of x plus h. There's a plus in there. Minus f of x. Still putting that guy in parentheses so that you don't make that careless mistake. All over h. So step one is to evaluate f of x plus h, which means I have 2 parentheses squared minus 3 times parentheses, okay? Turn that x into a parentheses and then drop in that x plus h and then do the magic math for it, okay? So I am going to take a little bit of an extra step here because I am going to have to multiply this by 2. But x plus h is x squared plus 2xh plus h squared. Okay. And then I have minus 3x minus 3h. I'm distributing that negative 3 through here because that's what my rule says. And this becomes 2x squared plus 4xh. Don't forget to distribute that 2 through there. Yes, I know. That's what you guys forgot. Minus 3x minus 3h. This is f of x plus h. Got a little bit bigger this time, right? But we're still going to plug it in here. And so now my difference quotient, 2x squared plus 4xh plus 2h squared minus 3x minus 3h. And now, oops, I forgot, didn't I? F of x, I forgot to write your f of x over here. That's 2x squared minus 3x. You may not want to do that. It does, I just think it's helpful. I just forgot it. And minus then my f of x. And then all of this is over h. Okay, I'm going to stop. Make sure your page looks just like mine. So please make sure your sheet of paper looks just like mine. Okay, you may not have the really pretty pink and green and blue colors, but otherwise it should look the same. All right. Let's clean this up. So 2x squared plus 4xh, 2h squared minus 3x minus 3h, and then I'm going to distribute this negative sign, minus 2x squared plus 3x, and all of this is over h. Again, if I've done this right, every term that doesn't have an x in it should disappear. X squared minus, 2x squared minus 2x squared, negative 3x plus 3x. Notice the only terms I'm left with in the numerator have an h in them. 4xh, 2h squared, minus 3h, all over h. And again, h will divide into each piece, and so I have 4x plus 2h minus 3. Sometimes you will see it written like this, 4x minus 3 plus 2h. That's okay also. Sometimes we just stick the h at the end. It does not matter as long as you have a 4x and a minus 3 and a 2h somewhere in that expression. It really does not matter what order they come in. That is my final answer. Questions? I think that's probably the hardest thing we're going to do today. Quite possible. Make sure that I'm not ignoring your chat. So hopefully nobody's chatting to me over here. That was such an issue the other day. Okay. So one of the things that I said a while ago was that to begin with, we looked at some sets of ordered pairs to determine whether those ordered pairs represented a function. Well, we can also look at a graph to determine if the graph represents a function. And since I told you couldn't have repeated x values, if you recall in section 2.3, we talked about what an equation looked like which had repeated x values. Now, I didn't say it like that, but that's essentially what it was. So if you recall, x is equal to a constant is a vertical line, right? So because a vertical line has repeated x values, a vertical line is a good test to see if the graph of a relation is truly a function. Short version of this is, if you've got a graph, draw vertical lines. If your vertical line touches more than one point, it's not a function, okay? Because if your vertical line touches more than one point, you have repeated x values, right? So that's all you got to do, okay? So I want you guys, I'm going to do number 8 for you, and then I want you to do 9 and 10 and determine function, not a function. And I want you to send me private message, because if you send it to everybody, then nobody else has to do anything. So send me a private message as to whether 9 and 10 are functions or not a functions. But I'm going to do number 8 for you. I'm going to draw an amazing looking vertical line. Check this out. There's only one vertical line here, and I can draw a vertical line here, and that's not quite vertical. I can draw a vertical line here and here. These are vertical lines. I promise they're vertical lines, okay? In other words, I can draw a vertical line through this graph all day long, every day, and it is a function. So number 8 is a function, right? So let's look at 9 and look at 10, okay? So you can say 9 N or F, and then 10 N or F. Oh, doing great. I just can't answer y'all fast enough. Yes. That was great. I'm waiting for a couple more people to answer me. And your answer can be simply, I don't know. That is an acceptable answer. Okay. I think I've got just about everybody needs this. Okay. All right. So let's talk about number 9 because several of you guys have pointed out something really, really important on number 9. Number 9 has one place that's concerning. Okay. Number 9 is actually a function. So it is a function. I'm not going to have repeated x values, but there is one place, and it is at x is equal to 2, that we have a little bit of a concern. And so let me see if I can draw my line, my vertical line through here. Okay. So everywhere else is fine. Draw, only touching one place. But right here, several of you are questioning what's up here. So what this means is that I actually don't have a point here at this open circle. I do have a point here at this closed circle. So I do not have an x value that has 2 different y values. However, if this had been a closed circle and this had been a closed circle, no more function. Okay? So that was just a little bit tricky, and so that's why I like to put that on there so that you make sure that you really do understand that. So, but the open circle says that there's not a point there, and the closed circle says that there is. Does that make sense for those of you who are a little bit confused on that one? Because I had several people who were a little confused on that one. Okay, if not, send me a message and say, no, I still don't get that. Okay. Number 10 is not a function. Draw one vertical line right there. All it takes is one, and I got an issue here, and I got an issue here. So not a function. Okay. All right. Makes sense. Questions. All right. Okay. Also, I was going to tell you on Thursday, we are going to do a different section, a new section on Thursday at the first half of class. But the second half of class, if you want to ask questions, either off the test review or off a quiz or off of homework or something like that, so give you a little bit of time, 30 minutes or so, to ask questions about material that's going to be on your test, just to give you a little bit of an extra time to ask questions. So keep that in mind too. So I don't know what made me think about that, but something did. So, okay. All right. So we've talked about functions, and we've actually looked at several. Most of our functions so far have been polynomial functions, but there's a couple of. So in this class, we really concentrate on 3 different types of functions. We concentrate on our polynomial functions. That's the majority of the functions that we talk about. We talk about some rational functions, and we talk about some root or radical functions. Sometimes those are called radical functions in that last one. And you just really kind of need to be able to identify these just by looking at the definition and saying, oh, that's a such and such, or oh, that's a such and such. And it also, depending upon what type of function it is, as to what the domain is going to be. And that's really going to be the big stuff we're going to be looking at. So a polynomial function, the domain is going to be any real number. And essentially, this is what we've been looking at, okay? Polynomial functions are things like f of x is equal to x squared plus 3x minus 5, okay? Or g of x is equal to 5x to the 4th minus 3x squared. There's a lovely polynomial function, okay? I could have a polynomial function called h, and it might be 1/2 x cubed minus 7, all right? So anything, excuse me, where I have an x to a whole number power, all right? X to a negative power, that's all bets are off. But x to a whole numbered power, that's going to be a polynomial function, okay? A rational function is a function that involves a fraction and has a variable in the denominator, okay? So it might be f of x is equal to 3 over x. That's a polynomial function. A rational function. It might be g of x is equal to x plus 1 over x minus 5. That's a rational function, okay? And the problem with rational functions is the denominator can't be 0, all right? So if I have a function of the form of g over h values that make the denominator 0 cannot be part of the domain. And so we'll talk about that when we get to these. The final type of function is our root or our radical functions. And for the most part, we're going to be talking about square root functions. So g of x might be the square root of x minus 5, all right? So in this case, we have to make sure what's underneath this radical is positive. And I'm going to walk you through the process of finding these different domains, okay? So I need you to be able to look at a function, recognize what kind it is, and then be able to identify its domain. So that's what we're going to do next. I put them in order for a reason, so I want these to match up. So hopefully you'll be able to quickly identify what kind of functions they are, and then we are going to talk about their domains. So number 11 here is a polynomial function. It has x to the fourth, x cubed, x squared, x, and a constant. There's no exponents that are fractions. There's no exponents that are negative. There's no square roots. There's no denominator. So it is a polynomial function. So we classify this as polynomial. And the domain is all real numbers. So negative infinity to positive infinity is just our interval notation for all real numbers, okay? And that's it. If you see a polynomial function, you throw a little happy dance party and say, domain, all real numbers, I don't have to do any work. My favorite, okay? Number 12 is a rational function. And what makes it a rational function is this x squared in the denominator, okay? We talked about restricted values when we were solving we were simplifying rational expressions, and when we solved some equations that had rational expressions in them, we talked about restricted values. We talked about what x couldn't be equal to. That's what we're revisiting. I told you we were going to put a whole bunch of stuff together in this lesson. And so in this case, the first thing we're going to do is identify it as a rational function, okay? Because it does have that variable in the denominator. Now, to find the domain, okay? So to find the domain, we're going to do step 1. Take the denominator and set it equal to 0. Well, x squared is essentially the same as x. And so if I take the square root of both sides, it's okay. I get x is equal to 0. This is the value that must be removed from the domain. So the second step is to remove this. We're really not, but we're removing x is equal to 0 from the number line, all right? And so what that means to me is that I draw a number line and I put 0 on it and say, okay, I have to remove that number. So I'm going to put a big open circle here, and I'm going to shade everything to the left and everything to the right. And in terms of my domain, how I write this is I say negative infinity to 0, union, don't forget your union, 0 to positive infinity. And that's what my domain looks like. So I'm going to stop here and make sure we're good. So whatever value makes the denominator 0, or values that make the denominator 0, we remove them from the number line, and then we get our domain. Questions? Okay. The last type of function is our radical function. And so we can either call this a root or a radical function. If it's a pull down menu, then you're going to pull down whichever one of these. They're the same thing, okay? So because it's got a square root around it, okay? To find this domain, this one's a little bit different. That's why we get very excited with polynomials, because they're super easy, okay? We're going to take what's underneath the radical, under the radical, and make it greater than or equal to 0. So I'm going to take, in this case, 4 minus x and set it greater than or equal to 0. And I'm going to solve for x. So I'm going to subtract 4 from both sides, and I'm going to divide both sides by -1, which flips my sign around, and I get x is less than or equal to 4. This is the domain, okay? So the domain transferred into interval notation is -infinity to 4 and a square bracket, because I can actually take the square root of 0. And that's it. That's how I find the domain of those 3 types of functions. Questions? All right. Y'all either absolutely hate this or you got it. You're amazing. If you're like, I don't even really know what to ask, you can tell me that in a chat. You can send it to me a private message and say, I don't even know what to ask. It's not good, but we can work with it. The big thing is to identify the type, and then this will walk you through the process of finding those domains. All right, so we want to talk about properties of a function's graph and lots of different things that functions can do. And once again, we're putting a whole bunch of things together here. Some of this we've actually really already talked about, and so that's why I always feel like this is a lot of material, but I do think it's very much a review of so many of the things we've talked about. So we talked about x-intercepts and y-intercepts. This is just a restatement of the same thing. So once again, just trying to put it all together for you. To find x-intercepts, we let y be equal to 0, and we find x. To find the y-intercept, we let x be equal to 0 and find y. I am going to point something out to you here that is special about functions. Functions will never have more than one y-intercept, period, okay? And that is because if x is 0, there's only one y value that goes with that, or it's not a function anymore, okay? Functions can have multiple x-intercepts, but never more than one y-intercept. That's big. Sometimes when you're asked to find the x-intercepts and the y-intercepts, you're going to have to read the question carefully, because sometimes it's literally going to list them. It's going to say like find the x-intercepts, and you're going to say x is equal to 1, 2, and 5, okay? And sometimes the directions are going to say enter your answers as ordered pairs, and you're going to have to write it as ordered pairs. And we've talked about this before, but I just wanted to restate that you really just need to read the directions on those type-in answers, okay? And that's on the quizzes, tests, homework, whatever. Read the directions. It tells you what it wants, okay? If it doesn't, then it becomes my fault, okay? The x-intercepts are also called the zeros of a function. And folks, I can't really emphasize that enough. So I need you to pay attention to the fact that if the directions say find the zeros, it's asking you to find the x-intercepts, okay? So a lot of times when we talk about functions, we talk about the zeros rather than the x-intercepts, and it's because we let the function or y be equal to 0 and we find x, and that's why they're called the zeros of a function. So the zeros of a function are the same thing as finding the x-intercepts, right? So just know that. And sometimes you're going to have a function that doesn't have y-intercepts, it doesn't have x-intercepts, and that's okay. That's fine. There's nothing wrong, okay? But like I said, this is really stuff we've already talked about. So kind of moving on through this. First thing we're going to do is just remember how to do this. We're going to work some problems. I like to give you lots of examples, okay? So this is a linear function. We talked about linear equations. So I do want you to identify this. It is polynomial, but in particular, it is a linear function, okay? So we can also put on here that it is polynomial. So that might help you just kind of re-emphasize that, okay? Polynomial because it's x's to the whole number of powers, linear because it's x to the first power. X-intercept, we are going to let the function or the y value, you can turn f of x into y. Y is exactly the same thing as f of x if that makes you happier. So we're going to take 2x minus 3 and set it equal to 0. And this is going to give us 2x is equal to 3 and x is equal to 3 halves. That is the x-intercept, or as an ordered pair, it is the ordered pair 3 halves 0. Okay, just one, that's all it has. The y-intercept, we're actually going to find, and this is just another way to write this, f of 0. So we're going to find the y value when x is 0. So 2 times 0 minus 3. So this is going to be 0 minus 3. F of 0, or my y-intercept, is negative 3. So negative 3 is my y-intercept, or I can write it as the ordered pair 0, negative 3. Okay? All right. We've done that before. The only difference is we're calling it f of x rather than y equals 2. Okay? Now, I've already tested on this. You got this. You're going to knock this out on this test. Okay. So the next one here, we have the function. This one is polynomial. Okay, so just keeping consistent with naming this. In particular, it is a quadratic polynomial because it's quadratic because of the x squared. Okay, so it's actually potentially going to have two x-intercepts because of that x squared there. So we're going to take x squared minus x minus 6 is equal to 0. Remember, we talked about that. So this potentially has two x values. This one will factor. If it doesn't factor, we can always use the quadratic formula to find the intercepts or the zeros, okay? So all of this stuff is coming together now. So remember, though I had to take each factor and set it equal to 0, I actually had to find out what x is equal to. So x is equal to positive 3. And x is equal to negative 2. And so we can also write these as ordered pairs, 3, 0, and negative 2, 0. So we do have two zeros or two x-intercepts. Only one y-intercept, all right, because again, otherwise it won't be a function. So I'm going to find f of 0. And so I have x squared, oops, I have no idea what I'm doing. I'm going to have 0 squared minus 0 minus 6. Everything's going to disappear except for the negative 6. So this is my my y-intercept. So y is equal to negative 6. Or I can write this as 0, negative 6. Questions? Okay. So now we're going to look at graphs, and we've talked about domains and ranges. We've talked about it in terms of, we talked about domains in terms of looking at a function. We've talked about domains and ranges, looking at the set of ordered pairs. So in this, we have a big set of ordered pairs. So we don't want to write all of the ordered pairs because while this particular graph points out to you 4 ordered pairs, there are an infinite number of points or ordered pairs along this graph, okay? So there's no way I can sit and list every single x value because there's an x value of negative 4.9 and negative 4.99 and negative 4.91 and negative, and hopefully you're getting the idea. There are literally infinitely many points. And so in order to write the domain and the range of a graph from the picture, we use intervals, okay? And so just like we did with the function writing the domain, we're going to do something very similar writing the domain based on the graph. So the domain, again, is the x values, okay? And we read from left to right, okay? The range is the y values, and we read from bottom to top, okay? So let's talk about the domain for this function. So the domain for this function, we start on the left side and we figure out where the first point is. And here is the first point, and I look at the x value, okay? And then I follow my graph, so I'm going to have a square bracket, and it's going to start at -5. And I'm going to follow my graph, I'm going to follow my graph, and follow my graph to the end. And here's where my graph ends. My graph ends at an x value of 3. And so my domain goes from -5 to +3. Okay. The range, I told you we go bottom to top. Okay. So on the range, I start down here at the bottom of my graph, my coordinate system, and I move up and I move up and I move up. And the first time I run into a point on my graph is right here. And this is my first y value. There are no points below the x-axis on this graph. And so my smallest y value is 0. And now I just keep kind of moving up my coordinate system until I find that I've run out of points on my graph. And so the last or the highest point on my graph is sitting over here, and it has a y value of 4. And so my range is 0 to 4. Questions? That one's a little tricky. Okay. So let's talk about the domain for this one. Okay. So this one is a little bit different. And then again, I'm still going to start at the left and I'm going to move across my graph to the right. Okay. This little vertical line right here is actually called a vertical asymptote. We'll talk more about this later on, but sometimes you run across them in graphs. It is a line that the graph gets close to but never crosses. So keep that in mind, okay? So this graph just keeps going up, but it's never going to pass this point. It's going to keep going up, but it's never going to cross here. Okay? So put in a chat to me what you think the domain of this might be. And you can either chat it to everybody if you think you've got it, or you can just send it to me privately. But let me see if I can get a couple of folks to give me an idea of what they think the domain for this function is. Okay. Some of y'all are super close. Some of y'all are so close. Nobody's exactly right yet. So close. So close. So close. That's actually a good way to say that. I like that one. Ooh, that one's almost there. Almost. I'm gonna tell y'all what the answer is. We're looking at the x values here, not y values. Okay? And we're looking at x values. Okay. So I think I've tortured you long enough. Okay? So let's talk again. Remember, we're looking at the x values. And so most of you realize that the graph started at this point. And that's fabulous. Except watch this. This is an open circle, which means that my parentheses are not going to be square. It's going to be round. Okay? So a couple of you recognize that and changed your minds, and that's great. And some of you had the square bracket there, so I need a -4 with a round bracket. And I follow my graph, follow my graph, follow my graph, follow my graph, follow my graph. It does go to infinity, but not on the x-axis. It gets super close to the x value of, and I love the way somebody said it. They said something less than 5. Yep, you got it. So, and how do I write less than 5? I write to 5 with an open bracket. This is an interval. It looks like an ordered pair. It is not an ordered pair. I am talking about the domain, so therefore it's implied to be an interval, but this is the way we write this, okay? We can think of it as -4 is less than x is less than 5. That's the way we can write it in inequality notation, and this is the interval, okay? All right, so be careful there. All right, so the second part of this talks about the range. The range is the y values, okay? And so as I'm moving up my graph, the very first point I run across is this one. Even though it's an open circle, it is the smallest y value, so we do start at -3. And here's the one, it just keeps getting larger and larger, and so it's going to be -3 to infinity, okay? Question. Some of you guys were so close. And that little arrow thing and that vertical asymptote are a little bit tricky there. Questions? Okay. Let's see what other fun things we can do. Okay, so when we talk about graphs, we talk about the things that graphs are doing, and we talked about lines the other day, and the fact that a positive slope was increasing or going up, and a negative slope was decreasing or going down. Well, our functions can increase, decrease, and they can be flat also. And a constant function is flat, and that's kind of boring. But anyway, we also talked about lines that were horizontal, and those are our constants there, so they're just very boring. So, and remember their slope is 0. Just tying it all back together. One of the things I want to point out to you is when you're talking about intervals for increasing, decreasing, and constant, these are always x-axis values, okay? So notice that my picture down here, which I stole from something I borrowed, I with permission, I borrowed, I didn't steal it. So, because I thought it was such a beautiful graph, I was like, can I use this? And they were like, sure. Anyway, so it shows you that my graph is going down, so it is decreasing on this interval, and we would say it's decreasing on the interval from A to B. These are x-axis values. It is flat through here, so we say it is constant from A to B to C, and then the graph starts to go up. So in this little interval from C to D, we say that the function is increasing. So this graph decreases constant and is increasing. Sometimes graph will do 1, sometimes they'll do all 3, sometimes they'll do 2 of the 3 things, all kinds of fabulous stuff, right? All right, so let's get started and see how many fabulous things we can do with this. Okay, so on these two we have pictures, and we just want to identify where the graph is increasing, decreasing, and being constant. And so this is usually what I tell students to do. Ignore these arrows. They are misleading. We don't want to look at them. They just say the graph keeps going, okay? So we're going to start here at the leftmost end of my graph that I can see, and I'm going to follow the graph. And in this case, my graph is going up, 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 and it just keeps going up until I get to a change. And here's a change. That's important. I am going to mark this x value. There's an x value where it changes, okay? Then what happens? My graph now goes down, and it goes down, and it goes down, and it continues to go down and down until it changes. and x value of 2 is a change. Okay? And then it goes back up, and it goes up, and it continues to go up until, in this case, it stops. And obviously that's going to be a change or a stopping point. Okay? So it has 2 intervals where it increases and 1 interval where it decreases, and no intervals where it's constant. Okay? So the first part where it's increasing is going to be the interval from negative infinity to negative 4. We use round brackets on all of these. And then it's going to be from the x value of 2 to the x value of 5. And that's it. Okay. We are going to separate these intervals with a comma. MyLabs Math tells you to put a comma in between them if you have more than one, so you don't have to use the union symbols. Okay. So these are my 2 intervals where it's increasing. Now it's decreasing on 1 interval, so it decreases from here to here, and that is from negative 4 to 2. Looks like an ordered pair. It is not. It is an interval. Okay. And then finally, it is constant nowhere. There is no interval where it is constant. Okay. All right, we're going to do the same thing with number 6 over here. Starting on the, don't look at the arrow. That's confusing and misleading. It's going to go down. And it goes down until it gets to this turning point. Okay. And then it starts to go up. And it goes up and it goes up until it gets to this changing point. And now it is flat. And it has the same y values for everything until it gets to this changing point. And then it goes down. And it just keeps going down. Notice I've got this infinity thing's going to happen here. Notice the only things I marked are the x values. Okay? All right. So there is only 1 interval where this function is increasing. And it increases from the x value of negative 3 to the x value of 0. That is not a point. Okay? It is a portion of the graph. It is the x values from negative 3 to 0. Graph is increasing. This is huge. You're going to get on the quiz and you're going to go, it's not doing anything at that point. And I'm going to say, but it says interval. And so you have to read, except I'm not going to be there to say that to you. All right. It is decreasing on 2 intervals. It decreases from negative infinity to negative 3. And then it decreases from 4 to infinity. We got those infinity things going on because of the arrows. And then finally, it is constant from 0 to 4. X values only. I'm not involving those y values. Useless pieces of information. Questions? Okay. So another thing we talk about with functions is turning points. And turning points are also known as relative maximum points and relative minimum points. And those are incredibly important as we move through some other things. They have some significances later on. I'm going to backtrack real quick to this particular graph. This particular function has both a relative maximum and a relative minimum. Okay, so this is its relative max, and this is its relative min. Okay, this function only has a relative minimum. It does not have a relative maximum. This 0.03 and this 0.43 are not maximums or minimums. They are turning points, but they are corner turning points. So a maximum, and I show you that so I can point this out to you, a relative maximum is where the function changes from increasing to decreasing, and a relative minimum is where the function changes from decreasing to increasing. At those corners on the previous page, it changed from increasing to constant and constant to decreasing. So maximums and minimums are changes from increasing to decreasing for your maximum. You climb up the hill, you get to the peak of the hill, and then you go down the hill. So that is your maximum. If you have a minimum, you decrease, you go down into the valley, you hit the low point of the whole hike, and then you go back up and you start to increase, okay? So maximums and minimums, increasing to decreasing, decreasing to increasing, changes like that. No constant to something and no something to constant, okay? So be careful there. Okay. So long question. I know there's only one of these on the homework, but there is one of these on the homework, and it actually has J pieces to it. We're going to get through this. I promise you're going to make it jump. Guys are amazing in this problem. You can do this, okay? So hopefully this is the one time when you're really going to wish that you printed off the notes. So sketch the graph or think, oh my gosh, I'm going to go back and print those notes off and we're going to work through this. Take a picture of it now, whatever you need to do. These are some of the problems you're really going to wish you printed those notes. So anyway, okay, so domain and range. So domain again is my x values. And so I am going to be hanging out here looking at the very first point I run into, and it is going to have an x value of -8. Here it is. Remember, it is going to have a round bracket there, though, because of the open circle. So -8, and it's going to go all the way to the end, and my graph does end, and it ends here at a value of 9. Please notice the difference. I am going to put a square bracket on the domain. My intervals of increasing and decreasing never, ever had square brackets. I hope that sank in. My intervals of increasing and decreasing always had round brackets. Domain can have square though. Range can have square. All right, and in fact, the range is going to go from the y value I first run into, which is at this point. So -5 with a square bracket, 2, and my largest y value is here at a y value of 3. Stop me if you need me to. Increasing, decreasing, and constant. So I start here and I follow my graph. Okay, so I follow my graph and it goes up, 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 up. Here's a changing point, okay? And then it's going to go down through. Yes, question? Okay, notice it's going to go down through this point here. That's going to be significant later on. And it's going to change here at an x value of -2. It goes back up. And it changes again. But it changes to constant. And then it changes again. And it continues to increase until I get to this x value. I do have changes here and here. And then it decreases until it ends right here. And that's where it stops. All right. So I'm going to have 1, 2, 3, 4, 5, 6 different intervals that are either going to be increasing, decreasing, or constant. And my x values that I've underlined are my x values I'm going to use in those intervals. Okay. So increasing is the first one. And we want to know where is it increasing, and it increases in 1, 2, 3 places. And so it increases from -8 to -6. It increases from -2 to +1. And it increases from 4 to 7. Okay? Only using the x values. Be very careful. Right? Decreasing. Where is it decreasing? Well, it decreases on 1, two intervals. Nice thing is this is going to be a multiple choice problem. Okay, on this, even in the homework, this is going to be multiple choice. It's going to say on which of these intervals is it increasing or decreasing or constant. So don't stress over the typing of things in. It's not going to be that bad. You just have to select the intervals. So -6 to -2, it's decreasing, and then it's decreasing from 7 to 9. Okay, so these two intervals. Notice I'm still only using these x values. And then finally, where is it constant? It's only constant on one interval, and it is constant from 1 to 4. Once again, that's not a point. These are all intervals. All right, D and E are asking about the relative minimum points and the relative maximum points. That's just plural for any of them. Sometimes you have multiple ones, and that A at the end is just plural for the UM. It's one of those Latin-y things. I want to point out that this question asks something a little bit different. It says, what is the maximum and where is it located? The location is the X part, okay? So keep that in mind. Location is the X, and the actual value is the Y, right? So this particular graph has one turning point on the bottom, one place where the change is from decreasing to increasing, and that is this point. So this is my relative, and I only have one, so it is my relative minimum. And so the relative minimum value is -5, and the location is at x is equal to -2, okay? So we say the value is -5, and it occurs at x is equal to -2. So the location is the x value, right? Now it actually has two relative maxima points, okay? So my relative maximum occurs here, and I also have a relative max here. Notice these two guys are not turning points, okay? And so one relative max is the y value of 3, and that occurs at x is equal to -6, and the second relative max is 2, and it occurs at x is equal to 7. Questions? Questions? Okay. Zeros. How many zeros does this graph have? Somebody tell me, how many zeros does this graph have? You don't have to tell me what they are, you just have to tell me how many of them it has. Getting lots of different answers here. And some of you gave me 2 answers. Not sure why a couple of you are getting 5. Kind of guess why maybe you're getting 3. Okay, so there are actually 4 real zeros. Okay, look at your ordered pairs. How many ordered pairs have a y value of 0? There are 4. 1, 2, 3, 4. Okay. If this had been an open circle here, then I wouldn't have a 0 at this point, but it is a closed circle even underneath my little green there. So if I had an open circle at one of those, it would not actually be a 0. But I do have closed circles, and everywhere the graph crosses or touches the x-axis, it doesn't have to cross it, it can just touch it here, okay? Everywhere it crosses or touches, I actually have a 0. And so my real zeros are at negative 15 halves, at negative 4, at 5, and at 9, okay? So I'm just going to list them like that. I'm just listing them out. I could list them as order of pairs. I'm just going to list them out, okay? All right? Y-intercepts, we only have one of those, and it is at negative 3. It's this point right here. It's the only place where the x value is 0. Remember, we can't have but one of those. Okay? Values where the function is less than 0. Okay, another way to say this is below, that's a B, below the x-axis, because that's where my y values, where the y values are less than or equal to 0. Okay, so I'm going to show you, I'm going to erase a bunch of these lines and things on here because I think I'm starting to, well, I'm not confusing myself, but it gets kind of messy here. So I'm going to erase these, just these little arrows, so that we can see what's happening here. See if I can do this without erasing anything else. Okay, perfect. Okay, so below the x-axis, or where my functional values are less than or equal to 0, are going to be, again, here, and all of this, and right here, because it says less than or equal to. If it didn't say less than or equal to, I wouldn't include this little endpoint here. So how do I write that? I write that as negative 8 to negative 15 halves. Now watch this. I have to include that because of the equals to here, okay? And then my next interval is from negative 4. I have to include it all the way to the x value of 5. And then I'm just going to write this one little x value all by itself in squiggly brackets, okay? Because it's just that one little x value where it's actually equal to 0. If that had been a less than 0 without the less than or equal to, then I would put round brackets on everything and I would leave this one off. All right, questions? Okay. So the next part of this says, where is this, or it says how many values of x make this function equal to negative 3? In other words, how many, another way to say this, how many points have y equal to negative 3? Okay. So one way to do this is to draw a line. Oh, no, you cannot see that. Never mind. Don't do that one. Let's go with blue. Okay. How many points does this line, y is equal to negative 3, cross? It crosses here and here. Why don't I include this point? Somebody tell me why I don't include this point. So the answer here is 2. Why don't I include this point? Because it has a negative 3y value. Why don't I include it? Or maybe should I include it? Should there be 3 places that have a y value of negative 3? I am open to suggestions. You're probably going to see something like this on the homework and possibly the quiz. What makes this point a problem? Nobody?
Open circle.
Yes, it's the open circle. Thank you. Somebody is paying attention to me. All right. It is the open circle. That open circle is causing me a problem. It is not actually a point. So be careful. Sometimes those show up at the strangest places, okay? Sometimes they show up in really strange places. Okay, this last one says, what is the value of f of 2? In other words, what is the y value? What is y if x is equal to 2? So I go to 2 on the x-axis. That's this x value right here of 2. I go find my ordered pair. It's right here. What is this y value? Somebody help me out. What is the y value for this point on my graph?
-1.
-1, exactly. Thank you very much. So f of 2 is -1, and that is my final answer there. Questions? I have a lot of stuff in one question. I tried to make several of the homework problems just kind of break this down into pieces, but I think there's one that's really long. I apologize. It's good for you. It teaches patience and endurance and I don't know, something else like that. Okay, these to me are the nice problems. This is where I revert back to when my children were in elementary school and they learned to fold things hamburger and hot dog style. I know. So you may have remembered that from elementary school. I tell students that if you can fold a graph hot dog style across the y-axis, to me that's kind of the long axis. It's not, but it feels like it. If you can fold it across the y-axis and everything lines up, then your graph is what we call an even function, okay? So if it's symmetric about the y-axis, it's an even function. If you can fold it hamburger, hot dog, and hamburger all at once, so make two folds, okay, and everything lines up, it's odd. So if it's symmetric about the origin in math world, then it's an odd function. Otherwise, it's neither. This is not going to be a huge concept, but it's on some of the questions, and you just need to be able to recognize it, especially the even functions. And so I'm going to give you some pictures, and you're going to identify them as even, odd, or neither, okay? So I want you to tell me, first of all, which one of these is the even function? You can type in 8, 9, or 10. Which of these is the even function? Even function. 8, 9, or 10. Yes. So far, so good. Yes. Yes. I think the rest of you have gone to sleep on me. Yes. Yes. Oh, no. Yes. I only got one no. Even. All right, some of you answered everything. Yeah, it's not quite right though. Okay, just want the even function. Okay. So if I look at these three graphs, 10 is the only one which is even, okay? Symmetric about the y-axis. Fold this graph on the y-axis, this one right here, and everything lines up, okay? Which one is the odd function? I don't mean odd by looking at it odd. I mean, which one, if I fold across the y-axis and the x-axis, would everything line up? Which one is the same thing in the essentially first mirror images across the first and third quadrants? Yep. 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 Yes. Okay. Incidentally, it happens to be the odd numbered problem up here. That's not why. But anyway, this is my odd function. It's the one, and these should be pretty obvious. Like I said, this is not a huge concept, but it is important. The even ones are probably more important than anything else. And then number 8 here is neither even nor odd. So that's just the way we classify it as neither. It's just a lovely, beautiful, fantabulous function. It just doesn't have any special qualities. Which feels so mean. My daughter was watching some show the other day and somebody told some little girl, "You have no special qualities." And I thought, that's horrible. Why would you say that? And now I'm sitting here telling this function that has no special qualities. I like that. Everybody has special qualities, just not one of these two. Y'all probably watch these same weird shows too. I don't get these. All right, how are we doing? I'm doing great. All right, I want to see something real quick. I have no idea why that's on there twice. That's the same page twice. I'm so sorry. We're only going to do it once. It just jumped in there twice. Sometimes strange things happen. Okay, so here's what I want to do. I'm really pushing time here, and there's just no way I'm gonna. I could finish this. I could rock it out and knock it out of the park, and y'all would be sitting there just staring at the screen like just really. This is what we're gonna do. We are going to do 3 problems, 1, 2, and 3, and then we're going to stop. Okay, which means that I want you to go ahead and start working on this homework. Right now, I'm going to leave homework number 6 due tomorrow night. If we get to a really bad place, then we'll start moving some stuff back. It may be that I move your test back to Monday, but I'm not 100% sure of that right now. So we're going to keep everything on the same schedule. But if I feel like I'm just really kind of just throwing stuff at you guys, then we'll stop and we'll postpone it. So, but right now we're going to stay on the same schedule, but I am not going to finish this section. I can't do that to y'all. Okay. But I do want to graph these because we've actually looked at some graphs before. And so you've seen probably at least one of these. This is a quadratic function. Its graph is a parabola, which is that U shape. And I know we talked about this before. My labs is probably going to give you a table of values and ask you to fill them in. It might give you this last column, or it might give you both of these columns. I like to give you this middle column to get you to the last one. If I square -2, I get 4. If I square -1, I get 1. I'm literally plugging these in. 0 gives me 0, 1 gives me 1, and 2 gives me 4. So I have my ordered pairs -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Okay. We've done this one or a very similar one to this. So, but I just have more points on here. So when I graph these, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. The thing I want you to remember is that it doesn't come down to a sharp point. It does curve. I know my graph is terrible. Sorry. Oh, that's horrible. That's so bad. Anyway, you don't get the cute smiley face on my Labs Plus. Only my Labs have. Only with mine. Sorry. But that's what my quadratic function looks like. This is going to be really, really important as we move through this chapter because you need to know that x squared is this really lovely, beautiful parabola that turns and actually has a relative minimum here at 0, 0. So this point right here is actually, in context of what we've been talking about, it is a relative minimum. All right, and I may have told you the other day it actually has a special name called the vertex. Okay. All right. Absolute value of x, backtrack real quick. Domain of this function is negative to positive infinity because it's polynomial. But the range of this function is actually 0 to positive infinity. Okay, it's only going to give me positive numbers. Notice I only get positive values here, all right? Okay. Wrong way, sorry. I can't punch buttons. Absolute value function is the graph of a V. So it is a V-shaped graph. It looks like this. It is two straight lines that come together at a point. The domain is still, it treats like a polynomial function. It is negative infinity to positive infinity. I can plug in any x value, and these are just nice x values, and I get y values out. So the absolute value of negative 2 is positive 2. The absolute value of negative 1 is positive 1. The absolute value of 0 is 0. Plug in 1, I plug in 2. And notice something about this. All of my y values, again, are what kind of numbers? Somebody tell me what all of my y values are here.
Positive.
They're all positive, exactly. Which means that my range, again, goes from 0 to positive infinity. So it looks very much like my x squared. It's just that the shape, because it's an x to the first power inside of here, my shape is going to be these two straight lines that come together. And so 0 and 0, and if I graph this, then my graph is this straight line here and this straight line here, and there's no curve to it. And so this is my absolute value of x. Okay. Now the last one that we're going to do today is the square root function. This is a root or radical function. And I wanted to do this one because we did talk about this. When we talk about the domain for this function, we have to set x, which is underneath the radical, greater than or equal to 0. There's nothing to solve, and so we simply say that the domain can only be these 0 to positive infinity. And so when I pick x values, I am only going to pick positive x values. Now you might be going, whoa, why 1, 0, 1, 4, and 9? Hello. I don't want to find the square root of 2. I don't want to find the square root of 3. I want to find the square root of nice perfect squares. So yeah, we put in nice numbers here. We can put whatever we want to. Okay. The square root of 0 is 0. The square root of 1 is 1. Those are nice. The square root of 4 is 2. And the square root of 9 is 3. And so I still get some really nice, it's just easier to graph if I have integer ordered pairs. It just makes life so much nicer on my graphing scheme here. So 0, 0, 1, 1. Now it comes all the way out here to 4, 2, and then 9, 3. And what this graph looks like is it looks like, and it actually is, it is a parabola that somebody turned on its side and chopped in half. Okay, so it is what I call a sideways half of a parabola. Okay, so they took the parabola, chopped it in half, and turned it sideways, and that's what it's going to look like. The range for this function is 0 to positive infinity. Okay, I am going to shut up because